So can you see my screen?
Yes, sir.
Okay, good. Okay. Just one sec. All right, so we were talking about LAN, local area networks, and we looked at several these two standards, this minimum frame size. So the 64 bytes, just remember, I told you what the calculation is somewhat, but you don't have to remember that. So it was originally 64 bytes based on the standards then, the speed, the delays in the repeaters and so on. And it has kind of stuck, but then when we go to 1 gigabit Ethernet, we'll see that it's increased a little bit. So I'll come back to this. So this is where we were. Looked at the Ethernet frame format, and as we have seen, there are two types. One is the Ethernet 2, which is kind of universally used nowadays in TCP/IP networks. And there is this IEEE 802.3, which is supposed to be used in conjunction with the IEEE 802.2 above it, basically. Okay. So the only big difference is in this type and length field. Yeah. So this type and length field out here. So recall that for Ethernet, this type field is, so you have the Ethernet layer, okay, and then you have other protocols sitting on top of this. We'll look at some of this, okay. There may be others. So whoever gives the data to Ethernet, this gets put into an Ethernet frame. Ethernet puts its own header and sent to it. But then on the receiver side, so this goes on the receiver side. So the receiver side, so this physical layer things comes, you get these bit streams out of it after decoding and so on. And then the Ethernet layer on the physical receiver side will get this frame out of this. How does it get a frame? So there is a line idle, and then it looks for this preamble bits. The preamble bits are there, it knows there is a start of a frame. Okay. Then it looks at the destination address. If the address is not this machine, this network card, it drops the frame, because then it's not for this machine, it doesn't need to do anything. If it is, then it will do the FCS check, okay, on everything up to this without the preamble. If the frame is fine, if the FCS match, then it looks at the type field. And the type field tells it basically who to give this data to. Whether you want to give it to IP or want to give it to ARP or something. Whose data is this Ethernet frame carrying? Okay. Whereas if it is a IEEE 802.3 frame, there is no such type field. Okay. There is a length field which says how much data, so you can identify the pad out of it. So you can remove the pad also. And then when we do 802.2 later, you will see this, who this data is for is kind of captured in this LLC thing. Basically. So this will kind of go deeper into this one and see what is. Yeah. But broadly, this is what you will see most often, this Ethernet. So this is Ethernet 2 basically. It's commonly called Ethernet. Okay. All right. And we have noted that the minimum frame size is 64 bytes, not including the preamble, sorry, including the preamble. So basically the data bytes are going to be 46 bytes. Okay, not including the preamble, sorry. So this 662 plus 4, okay, that is your 18 bytes. So 46 plus 18 is 64 bytes. So if your data that is sent from above is less than 46 bytes, then you're going to add the pad bits, which are all zeros basically. Then the natural question is, when it goes on the receiver side, how does the receiver see gets? Okay, so if it is more than 46 bytes, the receiver knows that there is no padding, because padding is only to make it up to 46 bytes. If you get a 50 byte data, then you know it's not padded. Okay, if you get something more, then also you know not padded. you cannot get less than 46. So you get 46, there are two possibilities. Either it is exactly a 46 byte data, or it was less than 46 byte data, but paired bits were added to it. So the question is then, how does the Ethernet receiver on the other side detect that and identify which part is paired and which part is data? So we leave that question out for some time. Remember that question, because there is nothing in the rest of this thing for an Ethernet frame for it to identify which part is paired. Okay. In IEEE 802.3, you have the length field. The length field tells you exactly what the length of this part is. So it knows this part, if I receive more than that, this is paired, so remove the last so many zeros. Okay. And the other question that I asked is, how does it know the end of the frame? It knows the beginning of the frame by looking for the preamble bits. So when it gets these 0101 things, okay, how does it know this is the end of a frame? So if your frame started, so just try thinking, how will you do it, okay? If this is your first frame, and then the next frame was here, okay? And remember, both of these can be variable sized because this data can be variable sized. So then you will not be able to detect exactly where one ended and where one the other one, because your preamble bits can also be there in the data. So you cannot just look for the preamble and say this is where, okay, preamble, therefore this is where it's ended. So what do you think? If I have to distinguish the end of the frame so that I can look for the start of the next frame again, okay, what do I need to do? Let's wake up a little bit. Try, at least guess something. Anyone? You understand the problem, right? I'm sending multiple frames. So on the receiver side, how can I detect when has one frame over and when has the next frame starting? Next frame starting, I know preamble. But I need to know when one frame is over so that I can start looking for the preamble. So how do I know one frame is over? Anyone? Anyone care to guess?
And maybe we keep on calculating the CRC as like each bit we examine and
No, you cannot do that. It's a good idea. Okay. So the idea is that I will calculate, keep on getting this and then calculate CRC as we go on. Okay. And then see whether it matches with something that I see out there. But first of all, you see CRC may not match. That is the purpose of the CRC, to detect the error. In that case, you should drop this frame only and go on to the next frame. Okay. The answer is here in this picture. This is something you cannot do, right? So all you do is to give a minimum gap between these two, bring the line down to whatever the definition of idle state is, okay, between these two frames. So there is a minimum interframe gap. So you cannot start transmitting the next frame right after transmitting the current frame. You have to give a minimum gap. And that gap is again defined by standard, is something like, I think, 9.2 microsecond or something. Not important for the fact, for you to remember the fact. So your frames will come something like this, then a gap, then something like this. Can be more gap because you may not have something to send out here. You may not have got the medium out here. But even if you are the only one transmitting, you got the medium all the time and everything, you must give a minimum thing in which you will bring down the line to idle state, whatever the definition of idle is. So I will look for the preamble bits from the idle, know the start of the frame, do this processing. As I said, I'll keep on looking for this until I get the line idle. When I get that, then I have got one frame. Now that I've got one frame, I will do that processing, as I said, calculate the FCS. If it matches, look at the destination and look at the destination address first. Not for me, drop it. Otherwise, calculate the FCS, do the type and all those things. Okay, so that's how we calculate the end of the frame. Now this MAC addresses, yesterday I just did this thing with 1, 2, 3, 4, 5, 6, 7, 8, 9. They are not like that. So you need to ensure that every MAC address of every network card, so MAC address associated with, so I will not use the term network card. Now onwards, I'll just start talking NIC. NIC is the standard network interface card. Okay. So basically, what is this? A 48-bit address. Okay. And the part one, so IEEE again, see these were the standards coming. So there is a vendor code. So you think of, some manufacturer of network cards, Dell, for example. Okay, Dell, HP, etc. So IEEE will allocate one unique 24-bit pattern to Dell, or maybe more than one if you have very large manufacturer. And when it manufactures its cards, on this it will put serial numbers out there. So that automatically makes all network cards manufactured by different companies have unique MAC IDs. So now you can just buy a network card from anybody, put it on your local LAN. You're guaranteed that all the network interface cards on your machines that are on your local LAN have different MAC addresses, which is necessary because, as I said, otherwise the same packet may be taken by more than one, which should not be so. Okay. And when we said broadcast should reach, this is what is meant by the broadcast. Okay. So say this is one of your addresses. So in that frame, okay, remember the DA field. Okay. So when the sender tries to send the Ethernet frame, in the DA field, it will put the MAC address of the receiver. How it knows the MAC address of the receiver, do not worry now. There's another protocol to find that out. We'll do that protocol later on. But all you need to know that somehow you need to know if you want to send to one specific machine in your LAN, you need to know the MAC address of that machine. How you know that? Do not worry. Then if you want to send to that one machine, you put that MAC address in the destination address field. And again, if the medium is shared, okay, we'll see other cases. If the medium is shared, then everybody who is sharing will get it. But then they will compare the destination address field with their own NIC's MAC address. And if it does not match, they will just drop the field. Only the one which matches will actually process it. Okay. But this is the thing. Instead of putting this very particular unique one node's MAC address, if you put all ones, all 48-bit ones, okay, this is interpreted as broadcast address. It's saying that it's for everybody. So everybody in the LAN will accept it and process it. And this is what is that kind of the definition of LAN that we have talked about, that if I send a broadcast, if MAC frame, an Ethernet frame with broadcast address in the DA field, which all machines will accept it? This will reach which all machines? Okay, those are the machines that are on the same LAN. That is kind of the definition of LAN. There are also multicast addresses where certain rules, but we are not going to go into that. So you should remember that this is the broadcast address, that if you want to broadcast, I'll put all 48 ones in the destination address field. Otherwise, if I want to send to one particular node, I will have to put the specific MAC address of the network card in that machine. Okay. How do I know that MAC address? We'll do it later. It's just what I just said. The MAC is unique for each LAN, the 48-bit vendor code given to NIC manufacturer by IEEE, serial number given by. So this is where you see the standards coming. So nobody has full administrative control, but you're supposed to play by the rule. You cannot just tomorrow put out a factory for manufacturing NICs and start giving your own addresses. So you have to suppose to there's a standards body, there's an organization which hands you these addresses. And if you want to manufacture network interface cards, you have to play by the rule, apply to that organization, get your vendor code. And then you are supposed to manufacture cards with distinct MAC addresses in that space. Okay. So all MAC addresses are unique. way later in, not in this course, but if you do networks a lot more, you can see there's a catch to this, but right now this is all you need to know. So every network card that is manufactured comes with a MAC address hard coded in it, and that MAC address, the way the MAC address is assigned, is going to be unique. You can guarantee that you buy from any two manufacturers, any two NIC cards from anywhere, the MAC address hard coded in them is going to be different. Okay. So then what happens? Now we have seen there are two different Ethernet formats. Okay, standards are the Ethernet 2, which we routinely call Ethernet only, and 802.3. So you will see here the term Ethernet for both basically. 802.3 is Ethernet standard and so on. So that's kind of a little bit thing, but you need to know that there are two standards: Ethernet 2, original Ethernet 2, which is the de facto standard now for TCP/IP. Okay, and 802.3, which has to be used in conjunction with 802.2. Not many people use it now, but it's there, it's still there in some cases, basically. Okay. So think of this problem. Suppose a machine receives a frame, okay, and there is this type length field. So how does this machine know? So think of a LAN in which some machines are using Ethernet 2 format. Their NIC cards are for Ethernet 2, and some machines are using IEEE 802.2 and 802.3. Okay, because you buy machines at different times and so on. So then, can packets, frames sent by one be recognized by the other? So the question basically says that if a receiver receives a frame, okay, this may be Ethernet 2 machine, this may be 802.3 machine, and so on. How does the receiver know, is this a Ethernet 2 frame or is this a 802.3 frame? Okay. And again, this playing by the rules, this standardization comes in. So Ethernet's maximum data payload is 1500 bytes. Okay. Remember, the length field in 802.3 is supposed to tell you this value of this, how many bytes of actual data you have without the packet. Okay. So what they did was this. And what is this type field? This type field was one code for each protocol that is using Ethernet that can possibly use Ethernet. So there's a code for IP, there's a code for ARP, and so on and so forth. Okay. So what they did was this: they assigned all these codes, okay, to values greater than 1536. Okay. So the max length field value in 802.3 frame can be 1500. So what the machine does is this: it looks at this field. If this value is less than equal to 1500, then it must be 802.3 frame, because there cannot be any protocol code with value less than equal to 1500 in the type field of Ethernet field. So if it is less than 1500, it's an 802. Less than equal to, it's an 802.3 frame. If it is greater than that, it's a Ethernet 2 frame. So if it finds less than equal to 1500, we'll interpret this as 802.3 frame. Look at the LLC PDU, give it to 802.2. If it finds the value to be greater than equal to 1536, we'll interpret this as Ethernet 2 frame. Look up the type code corresponding to whatever value is here, give it to that protocol software at the higher layers. Okay, and this is something we will not do. It's also possible because, to carry the type field inside 802.3, there's something called a snap header. I just mentioned this, but you don't have to do this. Okay, but if you are interested later on, you can do that. But again, not very important right now. But this is important. This is how you distinguish between Ethernet 2 and 802.3. So a receiver receiving a frame, okay, whether the receiver is of Ethernet 2 type or 802.3 type, you can put a software in there to check this and decide whether the frame received is of Ethernet 2 or is of 802.3. Is this clear? Is it okay up to this? Yes, no, please.
Yes, sir.
Okay. So slowly, as we, after this, we'll do something more, go to the higher layer slowly. You need to kind of start visualizing a little. You should start seeing a little bit in front of your eyes, the packets moving, this coming, this receiving, this processing, and every step kind of look at. See, suppose look at this thing, okay? The lower layer thinks about encodings, this physical transmission, encoding, decoding on the other side, okay? Up to giving you this bit stream of one frame is kind of in the physical layer and the hardware of the data link layer somehow. But once you have got this processing, this checking of FCS is also done in hardware. Okay, but just think, could you have done it? Could you have written a module for doing all these checks? If you think like that as if you are writing a software module to process this frame, okay, even if some parts of that frame processing like CRC check and all is done in hardware, okay, for faster speed, okay. But if you can think like that, you understand what exactly is happening. What is the need of the every field? Which field will you look at first? Okay. So at every step now, as we see, we go higher up in the layers and so on, we'll see lots of packets coming, receiving, sender, receiver. We'll talk about that. Start thinking when you kind of try to digest it. Okay, start thinking a little bit about, can I write a software for this? Can I write a function to process this? And so on. You don't have to, okay, but just in your mind try to visualize a bit. Some terminologies, okay. People may ask, so segment is a part of medium without any repeater. Okay, and one or more devices can connect to a segment. Segments can be connected using repeaters. I'll show you example of what a segment means. And just like we have a broadcast domain, which says if I broadcast, which all machines receive it, there's a collision domain, which says that set of devices at the simultaneous transmission by any two devices will cause a collision, which can be one or more segments. Why we call one or more segment, we'll see. So see, think of the simple examples we did in CSMA CD. This was actually the old days, the first LAN basically. You had a coaxial cable. So coaxial cable is, as I said earlier, it's like those cable TV cables, like your Tata Sky cables and so on. Okay, and you have tap points going to a room. So in a building, then this one cable will kind of, in termination, will kind of go through the entire building and so on. And at every room there will be a tap. I actually have a tap like this from very old days in my room in here. You come down, I will show you the tap. Okay, and you will connect it there. So this is a true shared medium. So here, any two people communicating will cause a collision, simultaneous communication. So the collision domain is basically all the machines, the entire thing. Okay, we'll see a little later that changes somewhat, quite a bit in the modern LANs basically. But that's the definition of collision. So next few slides, I'm just going to kind of give you some examples. You don't really need to remember all the details, but you need to kind of go through them to understand how do they differ basically. Kind of little bit, as I said, within 802.3 using CSMA CD, there's a large number of standards. And when you go out on the field, okay, you will hear 100 Mbps Ethernet, but if you have to design a network actually, you have to choose these things. Okay, and when I do switches in more detail, I'll tell you something more basically. Your cost kind of depends on everything out there. So very originally, these are not all the things. These are just a few examples. You have a 10 base T. T, as I said, is UTP. Okay, 10 Mbps baseband. Baseband means your bandwidth starts from 0, the frequency range. Unshielded twisted pairs, Cat3 or beta. That was the specification. Max segment length is 100 meters. Without a repeater, you can put at most 100 meters of things. So this is classic basically. This stays even now. So if you have to do a UTP wiring to design a network, you will not run a network where, let's say, from a room to the nearest switch, which is more than 100 meters long. You have to put a switch in between. Okay, because otherwise the attenuation interference is too large for this kind of things to work. Number of machines per segment is only one. Okay, this one we'll see. This you will not understand right now. These are some of the details. You don't have to remember. There's Manchester encoding, 1 persistent days. Okay, mostly not used. Okay, there are 10 Mbps Ethernet standard still, but 10 Mbps has become kind of obsolete. So too low speed. But again, you have industrial devices and all which still uses 10 Mbps. So this is the other thing. Okay, like we keep on having faster and faster things, and we keep on buying faster and faster things if we have money. But we don't always need that. So 10 Mbps cards will be, or 10 Mbps switches will be hard to find nowadays, except for special purposes. Okay, so you have moved on because cost has come down. Okay. But then when you have an option between, let's say, 1 Gbps and 10 Gbps, you kind of think, because 1 Gbps is a huge bandwidth still for most purposes. So still ask yourself, do I really need that? As I said, a full HD movie takes a few Mbps only. If only 5 users who are going to connect to a network and do something, you don't need a 10 Gbps speed. But anyway, 10 Mbps is almost not there right now. It is there for specific purposes, but for your general computer networking, connecting where you see buildings and so on, you won't see 10 Mbps switches. And this is just, you can look it up in the text also. So there were different 10 Mbps standards earlier. Okay, and you have everything. You have coax cables, you have UTPs, you have optical fibers. Okay, and this is the original one from which the 64 bytes came. You don't have to remember any of this, except maybe that 100-meter UTP. 100-meter UTP is very, very relevant even now, basically. Then came fast Ethernet. Okay, it's actually a group of 100 Mbps standards, same thing, 100 base TX, 100 base FX, and so on and so forth. So it's 100 Mbps baseband. So T again is UTP, unshielded twisted pair. Now it's Cat5 or better. Because higher the data rate, higher the frequency, higher is the chance of interference, basically. So you want to shield it better. Max segment length is still 100 meters. And it uses no longer Manchester. It is a 2-level 4P5P plus there's something called MLT3. Okay, there are variations of other thing, not TX, which uses NRZI also, that you study. And again, 1 persistency is missing. Again, you don't have to remember this. I just want to show you that what these standards mean, basically. So they have different encodings, different underlying physical layer details, and so on. And there's a lot more details. It's just like 2-3 very important ones. That's it. So here is again, you can look at basically 100 base important these things. You can look them up in the text also. I'm going to skip this. Then came 1000. Okay. So 1 Gbps. These are. I just wanted to tell you the standard names basically. Again, nobody remembers this unless you work with it every day. But when you see these things, somebody say 802.3U, 802.3Z, etc., you should be able to kind of intelligently talk about what do they generally mean. So there are a collection of standards around 802.3 for different speeds, different these things. Actually, there are different protocols to do with Ethernet also and so on. So now you see with, so this is one I picked up with a fiber, so you can see the distance basically. And with 1 Gbps, you do CSMA with some changes because, so this is where this thing comes up. So remember this 64 bytes thing for 10 Mbps, okay? And the slot time was 51.2 microseconds. So and this came from a distance of like each segment to be 500 meters into 5 segments with 4 repeaters. Okay? So slot time was nothing but how much time do you take to transmit 64 bits, put 64 bytes on the wire. Think of that as something is pumping out the bits on the wire at 10 Mbps speed. So this comes out to be 51.2 microseconds. Okay. So now, so this is with 10 Mbps. With 100 Mbps, okay, this you keep the 64 bytes the same for backward compatibility, but then you need only 5.12 microsecond to pump out those bits because it's 10 times faster. Okay. So what happened with this, to keep the same minimum frame size and still be able to detect the collision, you reduce this to 100 meters into 5. Okay. So to reduce this also, not actually not even 100 meters into 5. Okay. So total 250 meters basically. So now basically your propagation, your frames are going out faster. So your total propagation speed, propagation delay has to be smaller. Okay. So this is the sender, this is the receiver. Remember this total propagation delay, by the time this comes back to me, I should still be transmitting. So if I transmit faster, this has to come back to me faster. Okay. This has to come back to me within 5.12 microsecond, not 51.20, which means propagation speed remains the same. Okay, which means I have to kind of reduce this distance, which is what 100 Mbps did. Okay, and then for different reasons, we don't recommend more than 100 meters and so for each segment. Okay, now if I take this further into 1 Gbps, what will happen? What do I have to do? Anyone? So suppose I want to maintain the same 64 bytes minimum frame size. What will happen for 1 Gbps if this is what has happened for 100 Mbps? So my 2500 meter total length has come down to 250 meters here, roughly, so that I can detect collision even at the higher speed while maintaining the same minimum frame size. So if I now go to 1 Gbps and try to make the frame size the same, what will happen? What do I need to do? Anyone care to guess? It's simple. So now you will be pumping out the bits even faster, right? So it will be 0. Even 10 times faster than this, 5.2 microsecond for 64 bytes. So what needs to happen in order for me to be able to detect collision in CSMSE? Come on, guys, somebody. Did you understand what I said about the 100 Mbps thing? I really want to know, because in an online class, very difficult to get feedback. I don't want to move too far ahead if you did not understand. We will deal on this some more. Did you understand why this 100 Mbps thing reduced this to 250 meters from the original 2500 meters? Yes or no? Can you hear me? Hello?
Yes, sir.
Okay. So did you understand why this 2500 meter came down to 250 meter? When I went from 10 to 100, but tried to keep the minimum frame size the same?
Yes, sir.
Okay. So then if you apply the same principle, you try to go from 100 to 1 Gbps, which is even 10 times faster, and you try to keep the same 64 bytes, what will happen?
Maybe 25 meters.
Exactly. It's as simple as that. So max distance becomes at most 25 meters, okay, or even less than that practically. Okay? This kind of theoretical thing. But then that is too small. If you say that all my machines should be connected with maximum without putting a switch, I have to put a switch every 20 meters or so, that becomes too low. So 1 Gbps actually changes this to 512 bits, okay, with something called carrier extension. We will not do this, okay, but you may want to remember this, that 1 Gbps, the minimum frame size changes. Okay, and there's a way to kind of detect at the other side, even if the other side has 100 Mbps thing. So, you know, to kind of take out the carrier extension, similar to PAD. It's something similar to PAD, not exactly. But so as you go for higher speeds, your basic CSMACD is this thing, or basic, you know, the backward comparative starts breaking down a little bit, basically. Okay. This is again a picture that you can see that, you know, with 1000 base also I can use with copper. But typically that distance is very small, usually less than 50 meters usually. Okay. And with higher category thing, this plane shielded cable 25. So basically it's 30-40 meters that we use. So typically we'll use this for connecting, like, you know, servers to switches or something, where servers are usually closer to switches and so on, but not really for your network connection like you're in hostels or something. Okay, what about the physical interconnection between these machines in a LAN? I want you to pay attention, because these things are going to get some more confusing at the end of the class. Okay? So originally was bus topology with multi-drop lines. This is the one that I drew. Two terminations here, okay, and then you had, so the same wire will snake through all the rooms and so on. One long connection with taps to connect machines. Collision domain is all machines. You understand it's inflexible wire. Just try to visualize like CSE building with single wire with taps going. And now in one room where I had one point, I want to have another point, or I want to route, you know, added a new room somewhere. Then you have to cut the wire, then take this out, and so on and so forth, basically. So it was there. Nobody does coaxial wiring in buildings nowadays. Okay. It's just for historical reasons out there. And now comes this interesting thing, which was there. Or you can build a star or a tree topology with hubs. So this was there. This is the topology that is there still, but not with hubs. So what is a hub? Its hub is something that looks like a switch that you have seen nowadays. You'll have ports out here, okay, and you can connect through your, like, LAN cables, one machine to each port. Okay, but here is how a hub works. It is just a nice way of doing that wiring. So like this 10 base T and all, what will happen is in your building there will be central kind of wiring closet where I will put the hub. Think of that as your switch box where you see in the hostels, basically that big box with switches in it and so on. And so from every room, I will run a wire to this. This is where the star topology comes in. These are my rooms, room 1, room 2, and so on. Okay. But then the working of this device is exactly the same as if it's a shared media. So what it does is this. A frame received on one port is always broadcast to all ports. So logically, it is still the same as a bus topology, because anything that is sent by one machine is sent to all, is received by all. But it repeats the signal. It's like a repeater. Okay. Wiring is easy. Okay. But a hub is just repeating the signal. It operates at the physical layer. It gets the electrical signal, amplifies it, and just sends it to all the other ones. It's as if, basically, if you just think about this, it is as if this is like one big wire to which all of them are connected. Only thing, I have put this part basically into a single hub. So this is what was omnipresent till about, probably 15 years back and so on in the edge LANs basically, because switches were costly. Okay. So this was hubs. And then I can just extend it to have hubs with hubs. But this basically means if I send something here, okay, it goes here, 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 here. It goes everywhere. The entire thing gets a thing, basically. Okay. Now comes what is there now. Well, start tree is the same thing, but now with switches. Okay, it looks the same as hubs, as you know. The ports and two ports will connect these machines. But the big difference is this. It's not like a dumb device at the physical layer. Okay. So I here come layer 2 switch. Okay. You will see a layer 3 switch later on. There are also layer 4 switches. Okay. So when I say layer 2 switch, it means it switches, first of all, not repeats, based on layer 2 information. That's why it's called a layer 2 switch. We'll see what. Whereas a hub is a layer 1 device, physical layer device. It just gets the electrical signals, just broadcasts it to everybody. Okay. So what will a switch do? A frame received on one port is only sent on a port to which the destination is connected. How we'll see. So if I have, just look at the previous figure, or let's not do that. If I have this, okay, and there are machines 1, 2, 3, 4 connected. If one sends to 4, the switch will find out which port 4 is on and will send only to 4. Okay. So now basically what you got logically is a point-to-point topology. Just try to understand the difference. When it was a hub, if one is sending to 4, nobody else can send anything to anything. 2 cannot send to 3, 3 cannot send to 4, nobody can do it. But with a switch, if one is sending to 4, 2 can send to 3. Okay. So collision domain has become one machine basically. It's only that one other machine to which you are communicating, which can be converted. Again, that we'll see with a full duplex that disappears. And then I can extend this by interconnecting the switches in a tree topology, same as hubs. We'll see a bit. Okay. So switch will also repeat the signal, just like this, but it won't repeat it blindly to everybody. It will also look at the MAC address. That's the layer 2 information I'm talking about. So it operates a data link layer, layer 2. And based on the MAC address, it's going to say, oh, this MAC address is machine 4 MAC address. Therefore, I will only send this signal out to this. I won't send it to this. So 2 and 3 can simultaneously communicate, 1 and 4 can simultaneously communicate. And usually I will full duplex. So 1 and 4 and 4 and 1 can also simultaneously communicate. Just think of 2 pairs of wires. So the transmitter here is connected to one wire, receiver connected to one wire, transmitter here is connected to one pair of wire, receiver connected to one pair of wire. So one pair of wire is used between transmitter to receiver here, one pair of wire is between transmitter to receiver. Okay. So almost all LANs that you see are switch LANs now. Actually, it's almost, you can still odd cases, but difficult to buy hubs because switches have become so cheap. Okay. But that depends which switches we're talking about. The end switches that you see that directly connects your, let's say, room LAN point and so on are so cheap nowadays that hubs have disappeared. Okay. But then how does the switch know which port 4 is connected to? So one has sent a frame. Again, think about the frame. In that frame's DA field, there is an address 4. Okay. It has come to the switch. How will the switch know? Because you have just plugged in a wire. How will the switch know which port out of all these other ports is this address 4 machine connected to? Anyone care to try? Yes, no? Design yourself, try, guess. Okay? Think something, whatever comes to your head. No problem if you're wrong. All I'm trying to point out is you can mark the information that we teach, or at every step you can ask questions and say, how am I going to do it? And try to see and then try to compare with what they have done. Over a period of time with systems, over a period of time, you will see the benefits of understanding. So anyone care to try? Offline class, I can force you to try. Online, I cannot do that. You understand the problem, right? I bought a switch from the market. Okay, I just connected some wires to it. And now this machine 1, whatever its MAC address is, has sent a frame with the destination address, MAC address of another machine. How will the machine know? Out of its like 24 ports there and so on, which port to this machine is connected?
So the NICs probably broadcast their MAC address.
One possibility good. That was so one possible design can be very good. One possible design can be that moment I connect a, let's say your laptop with this, okay, the NIC will tell the switch what its MAC address is. That can be a protocol, yes. Okay, but that's not done. Okay, because you may keep on changing things and so on. No particular reason. That's a good protocol. Okay, every time I connect it, will tell the NIC, so the NIC knows basically. So what the NIC does is that it discovers, it learns. So at the beginning, it knows nothing. Just think of a fresh switch, and I've connected all of this, let's say these 4 ports out there. Okay, so NIC knows nothing. So first it gets the ones packet. Okay, it just broadcasts, just behaves as a hub and broadcasts to everybody, because it does not know where machine 4 is, which port machine 4 is connected to. But then it has learned something in the process. Can you guess what did it learn? Remember the frame format. There are 2 addresses here. There's a destination address, there's a source address. So what has the machine, what has the switch learned when it broadcasted one's packet to all other ports? It has received this frame from 1. It's right in front of your eyes. If you look at the frame and think that this frame, this is what I mean by visualizing, that this frame is received by the switch and the switch has processed this frame. So at the end of processing, it does not know where 4 is. So it has to broadcast to everybody. But it knows something now for future. What does it know?
It knows what 1 is.
Exactly.
Yes, sir.
Exactly. So it knows which port is 1, what is the MAC address connected to port 1. So its empty table now has one entry saying port 1 is this MAC address. So after everybody has sent at least 1 packet, okay, you kind of know the entire thing. So that's how a switch works. You don't have to do anything. I'll come back to this picture.
Sir, I have a doubt.
Yes, go ahead.
What will happen if we change the port? If we
Then you have to learn again. You don't go.
okay, sir.
Okay. So then again there are, okay, I said this is not done about this thing, but there are other protocols keep on going on in the backend. We'll look at one of them. So it's not necessarily that you have to send data to for the switch to learn. There are other backend protocols that keep on happening. Okay, we will look at one of them basically. So this switch getting a packet from each machine in each port will happen very fast basically. So this is what a switched Ethernet is. Frames no longer broadcast always, send to only ports. So separates a single collision domains to multiple ones, allows more than one pair to communicate simultaneously, increases the bandwidth to each machine. I'll just show you a picture for this one. Okay, and this is the how the so keeps a forwarding table, and we just describe how the table is built. So entries of the forward port, destination MAC address. So just as it receives a packet from everybody, it will just keep on. And even if your laptop is not sending, you are not actually sending any data or something, we'll see there are backend protocols that keep on running that your laptop communicates with the switch. So the switch will get some packet from you very fast once you connect this thing. Okay. And what about this increases bandwidth available to each machine? Take a look at this picture. Okay. This was your original shared. Okay. So it is total 10 Mbps, only one node can use it at any one time. Okay. When you did hub, so this is a hub, okay, your total capacity is still 10 Mbps. So by total capacity, I mean, if I look at this entire thing and I see what is the total amount of data that can possibly go between any, in this network between machines. Now, in both cases, because they share, this is just a better way of varying. Okay, maximum data rate can be 10 Mbps. But you see, now if I put a 10 Mbps switch out here, okay, while A and B is connecting, okay, so there is a 10 Mbps connection going through here. There can be another 10 Mbps connection going through here. Okay, and if you have full duplex, which is usually the case, as I said, if you have two pairs of wires connected transmitter receiver on the other side, which is the normal case now, you have 10 Mbps in this direction and 10 Mbps in this direction. So basically, if you have n ports, okay, the total data that can be moving around the network at any one point of time is n into 10 Mbps. 10 Mbps, as I said, is obsolete now. It can be n into 100 Mbps or n into 1 Gbps, theoretically. So switched Ethernet is good. Switches were there for a long time. Backend things were always switches. Okay, but then your switches were costly in the old days. Hubs were cheaper. So for kind of edge users like connecting our rooms with the next level thing and so on, people used hubs a lot. Or you have 5 machines, one machine and one laptop in my room I want to connect. So if your data rate need was not too much or something, you used hubs. These hubs were cheap. But now hubs are almost non-existent. For everything we use switches. You can buy a switch for like as low as 600, 700 rupees also. Small switches that sits in my office, for example, connecting my 2 machines and my laptop and I bring it and so on. Okay. So this is what I just mentioned, the switch learns. And what if we wanted more switches? Okay, let me just draw it. Okay, there's an example there. So suppose I want to connect 16 machines. Okay, but I have only 8 port switches. So many different possibilities. So I can do this. I can have 2 8-port switches. Okay, I can say 7 ports to machines, 7 ports to machines. Okay, and then this one port I take and put into another switch. Okay, so I have 7, 7, 14 things. So these 2 ports to machines. Okay, we could have done it in other ways also. All right. So now what will this learn? Basically now you see for each of these ports is a single MAC address, but for this port actually any MAC address in this 7 plus 2 9 machine should go to this port. So it's the same thing basically. Only thing that happens is that your table now instead of a single port to a single destination MAC, becomes a set of destination lines. So for this port, if it is port 8, I will have an entry like port 8 equal to, I will have all the max of this and this. And as and when I receive the things, so suppose this machine here sends a packet to this frame to this machine here. So this will come here. This will, suppose this is already learned. So this will come here. This will come here. Initially, it will be broadcast. Okay. Now, when it comes here, basically, remember that SA field is intact. So it knows basically this one, this MAC address has come through this line. It doesn't know what the rest of the architecture is. So whenever it sees that particular MAC address, it will just send it out to this. So we'll just add it to the port 8's list basically. Earlier, one port was one machine. Now it is one port can be more than one machine. Anything that, because a switch can be connected to one port also, which can be connected to more than one machine, other switches and so on. So this does not need to know anything about how this rest of the thing is connected basically. But you learn the same way. Okay, so this is just explaining that basically. But there is a issue here. Okay, so do you see? So this, suppose these are 100 Mbps switches. Okay, so I said that this can send 100 Mbps, this can 100, this 100, this 100, this 100. Okay, but all of them have to go out through this. If all of them send something to this, so do you see a problem? Anyone?
Bottleneck.
Exactly. Good. Okay. So if I make this also 100 Mbps, okay, then if all of them try to send to 100 Mbps, okay, then there will be a bottleneck here. Okay. Hold that question. I'll come back to the end of the class when I summarize. I'll tell you what happens in modern day switches basically. But you can connect, you can communicate. Okay. Bottleneck aside. Okay. Now, the thing is that, so the topologies that you just saw, okay, all these pictures that I drew and earlier pictures and so on, they're all tree topologies. Okay. But the problem with tree topology is always, so this can be switches and so on. The problem with tree topologies can be, if one of the links breaks down, then this, this entire part may actually go. If this link goes, then this entire part will go off. Okay. So this is not, tree is never very what we call fault tolerant, because breakage of one link, okay, can disconnect the complete one part of the LAN completely from the other. Okay. So for practical reasons, mainly for failure reason, the interconnection between multiple switches may not be a tree. So I can actually connect the switches in arbitrary topology. Okay. So there can be more than one path between two switches. Okay. And now I have a problem. The problem is something like this. Just think about, there are machines connected to this, but the switches are connected like this. There are machines connected to each of them. Okay. So now, suppose one of the machines sends a broadcast frame. Okay. So then sends a frame with this DA bit equal to all ones. Okay. So this will broadcast. Okay. So this will broadcast to this as well as this, because now there is no switching. Broadcast frame is going to be sent to everybody. Okay. Now this will send to this. This will send to this. Now what will happen? What do you think? Now this will send to this again, right? And if you think for a second, if you think about the packet format, there is nothing in the packet, the frame format, not packet, frame format, okay, the frame header, there is nothing to distinguish two frames. It's always theoretically possible 2 frames may carry exactly the same data. But they're exactly coming from same SA, same DA. Okay, it's coming from the same SA anyway. Okay. So for an arbitrary topology, the problem that may happen is a broadcast frame may go on forever. This is what is called a, this term is used in different contexts, but also called a broadcast stop. So this unnecessary frames moving around, okay? Because switches have no way of distinguishing that this frame has already been broadcasted. So what could you have done? As I said, you can mark the headers, or you can think when we go to IP, we'll see an IP packet can also travel for a long time, but not forever. So suppose I wanted to stop this. May not be immediate, but after some time. What could you have done? What if I want to stop it immediately? So a switch never broadcast a frame more than once on the same link. Because now this will come here, then this will send it again here, and this will circulate. Okay. What could you have done? Anyone? So what does this, when this broadcast thing comes here, okay, or it has come here, so this, what does this switch needs to do, or this switch needs to do to detect that it has already broadcasted this? It's not in your Ethernet frame. I'm saying, what could you have put in your frame header to stop this? Anyone cares to try? So one simple thing I could have tried to do is to put an identifier in each frame. But then just think about the problems, okay? Suppose I put an identifier. First frame that I send is frame 1, then frame 2, then frame 3, and so on. What is the till how long? What is the number of bytes I allocate to this? If I allocate too many bytes to this, okay, then that's an overhead. And that overhead is going to be used only for this broadcasting, nothing else. Only if you don't have a non-tree topology and so on. But for other frames, it is not needed. But you still have to keep the frame format uniform. You still have to put it something with it for every frame. And if you make it too small, okay, it will wrap around very fast. So there's a 2 bits, then 1, 2, 3, sorry, 0, 1, 2, 3, and then 0. So you will not be able to distinguish between this 0 and this 0. So putting an ID to detect duplicate frames is a bad idea. So not done. What is the other thing I could have done? I could have put, basically, I could have put a bound on this saying, okay, I will add a field, okay, count field here. When I create a frame, it will be 4. When the frame goes through every this thing, it's going to reduce this to 3, 2, 1, and so on. When it is 0, I will count. So if I know some maximum bound on the number of switches and so on, then I can actually do this. We'll see, we'll do something like this in IP. But it requires some assumption as to what is the number, what is the bound, the initial thing. So if it is 32, that means you can go in 32 times. You can go through 32 switches. Each of them will decrement it by 1. Okay. And when it comes to 0, I will drop it, knowing that it has gone through a lot. But then you need to know some bound on what is that thing, basically. Because again, in your header, you have to put a fixed number of bytes for it. So Ethernet does not do all that, okay, because that's more processing at the lower layers. You have to look at the packet, change it, and so on. Changing is always a little more time consuming and so on. Okay, but Ethernet will do something else. Do you understand this? Is this argument clear? Yes, no?
Yes, sir.
Okay. So what is done is there is a protocol that runs in the background called spanning tree protocol. Will not go into details. If you do that Wireshark thing on your machines for some time, you will see the spanning tree protocol packets going around. Okay. So what the switches do at the beginning when you connect a switch, they broadcast their switch IDs. So everybody knows everybody's switch ID at the beginning. Okay. And this is an ID, so I know whether I received the ID already and so on and so forth. And then by default, the switch with the lowest MAC address elects itself as the root. Okay. Can be configured by the administrator also. Usually lowest MAC address is default, but we do configure because lowest MAC address is not necessarily a good idea. Okay, because if you have a large network of switches, you want the root switch to be kind of in the middle because everybody is, your keys, so then the paths will be kind of equidistant. But then if you just take the lowest MAC address, then just by chance, okay, the switch basically, maybe one end switch becomes the root switch, okay, what's called the root bridge. And then everybody will have to transmit to that. So we don't do that. Each switch then finds the shortest cost path to the root bridge. Okay. So that's the protocol. You send packets and all to find a path. We are not going into that. We've got a simple Dijkstra-like protocol basically. So the root starts it, and then the packets go, and then everybody finds, adds the cost of the link with the cost of the link that is carrying in the packet, and so on. And then, so if you think about a switch, this is your root. You think about this switch, it selects one path as the lowest cost path. So then this port, okay, so this is basically two ports. This port it puts in a blocked mode, and this is the forwarding mode. So as long as this port is alive, okay, it's going to forward data packets only along this port. The blocked port is there just for redundancy. In case it finds that the other port does not respond, then it's going to put this in the blocked mode and then maybe make this as a job. But if there's more than such port, it will do the election again. Not election, finding the lowest cost path. Okay, so a simple spanning tree protocol. But the idea is, if a switch is connected to other switches with more than one port, okay, only one port is used for forwarding, the others are put in the block mode. If there is a problem with this port, then one of these other ports are chosen for forwarding. Again, you will find the least cost path and you will. And you periodically exchange what is called bridge protocol data units to monitor the topology. You reconfigure the links if the path is broken. Details are not needed for you, but understand that I can connect the switches in a non-tree topology, but that means that has this broadcast problem. And therefore, even though your connection, physical connection is a non-tree topology, at any point of time, the working topology for forwarding packets is always a spanning tree. And there's an underlying protocol which builds the spanning tree. Types of switches, I'll come to this at the end, okay, when I summarize. And then you will see in textbook these terms called bridges. Okay, not just textbooks, okay, you will see it here in other contexts also. So bridge basically is something that connects by definition more than one LAN segment. Okay. Now, which are these two LANs? Okay. Its purpose is to connect two LANs. They can be of the same type. It's called transparent bridging, which means whatever the packets from here, it will just transmit to here. No modification, no encapsulation, exact bitwise copy. MAC frames are relayed, so no LLC needed. Anyway, Ethernet does not use LLC. And you have buffering to meet peak demand. So there's a lot of traffic coming from here, but you cannot forward it fast enough. You have always have a buffer. This buffer thing is going to become omnipresent in networks. All LANs can be of different types, non-transparent bridging. Okay, so you can, for example, send from a 802.11 network to, a standard Ethernet. In which case, the frame format of this has to be translated to the frame format as per some rules, and the same vice versa for the transmission base. We consider transparent bridging. So non-transparent bridging is still there. But transparent bridging, you will understand what is the thing. Okay. So it says if you look at this picture, this looks like the same as switches basically. So frames with here in this picture, addresses 11 to 20, okay, are going to be repeated on LAN, and 1 to 10 are going to be. So this looks like very similar to as if I have connected a switch with machines 1 to 10 here. I have connected a switch with machines 11 to in the modern days 20 here, and there is another switch connecting these two switches, which is this switch out here. This is the same thing, basically. Okay. And then if you look at how does a bridge know which frame should go, again the same routing table similar to switches. How is the routing table built? You can be fixed and manual, or you can automatically learn it same way as address learning. So a transparent bridge actually looks very similar to a switch. Are they different? Are they same? Depends on who you ask. Okay, I kind of encourage you to go to Google and search with difference between switches and bridges, and you see how confusing the issue is. Because bridges had a very clear meaning in the old days. Non-transparent bridges still have very clear meaning. Because there are two types of LAN, even though number of types of LANs have decreased, but still you have to transfer frames, you have it. You see in your home access point a bridge mode, for example, when it bridges from your other Ethernet to this, basically. But then for transparent bridging, it's basically connecting LAN segments have become kind of connecting with switches and so on. So there are differences out there basically. So you can still say that if I broadcast, if I think of this as a separate LAN and this is a separate LAN, okay. If you broadcast in this LAN, it should only reach these machines. If you broadcast in this LAN, it should only reach these machines. Okay. As opposed to the architecture that I drew, where if you broadcast, it should go to all the 20 machines. So from that angle, there is a difference. Okay. But again, if you think about how switches are connected nowadays and so on, you'll find that this, people kind of think of transparent bridges are similar to switches. But there are small differences, technical differences, but you cannot really go by transparent bridges that much anymore, basically. So this is one of the confusion that you will have. But then again, people will ask you bridges, ask you switches, and you may get, at least for some time, what is the difference between a bridge and a switch from some old timers and so on. And the only difference that I could reasonably give you is this, that bridge still thinks of these two LANs as separate entities, separate LANs. And if you look at the definition of LAN as a broadcast domain, then if you connect them with bridges, the broadcast will go only in here. For this LAN, the broadcast will go only in here. Whereas if you look at this as a switched LAN with one LAN basically, then the entire thing will go. A broadcast from any one of them will go to the alternate basically. And finally, this is one term that you need to be aware of. This is called auto negotiation. Okay. So you have seen this 10 Mbps, 100 Mbps, 1 Gbps, all those things. Okay. So let's say you have an old machine. Okay. You have an old machine with a 10 Mbps card somehow. Okay. And you have some machines with 100 Mbps cards. Okay. And then you buy a new switch and all the ports are 1 Gbps, just suppose. Okay, and you connect them. So this port is capable of operating at 1 Gbps. But this one, the other end, is only 10 Mbps. Okay, and I told you 1 Gbps frame format is slightly different and so on. Okay. So there is a protocol underneath that runs whenever you connect this thing with this. There's an auto negotiation protocol, which basically says that you can turn it on and off. You can turn this facility on and off. Basically, it exchanges their abilities, and the highest common ability of two devices chosen. So at 10 Mbps and this will work in 10 Mbps. You could have had the other way around also, which is more dangerous. You could have a 1 Gbps thing, okay, and then the switch may be 100 Mbps ports. In which case they will fall back on 100 Mbps. So auto negotiation is a protocol that if you connect a machine with a switch port and the capabilities of the machine's NIC card is not the same as the switch port, then they will automatically negotiate the common ability, highest ability among them. By ability, most often it is the speed and therefore the associated frame formats and so on, if applicable. Yes. Is it clear up to so this? Okay, there is an LLC. We'll come to this. Is this clear? Okay, LLC, I'll quickly do. As I said, it's not used much anymore. It used to be used. Okay, almost everything that you will see is Ethernet 2. But here is what it is. It's 802.2. Provides a common interface to higher layers for data transmission, as I say. Okay. And it provides the optional link control facility. Remember, we talked about this data link layer, and it's everything, framing. Okay, it has medium access control, error detection. Okay, then it has flow control. It has error control. Okay. So Ethernet does only this, not this. 802.2 does this. Okay. But on top of plain Ethernet, I don't put 802.2. But if I do 802.3, it will do this thing here and this thing out here by 802.2. And if you look at that 802.3 frame format, remember there was an LLC PD that I can easily separate out because the length will tell me exactly what the length of this is. And this is what this. So basically, the DSAP SAP is like those protocol codes in the type. It says which protocol should process this. This is which protocol sent it. Okay. This is the actual data. There are some control fields that we don't need to worry about. So now basically 802.2 will look at this, and based on some other things, we'll do some flow control, error control, and then similar to type field, it will give it to the DSAP field, the protocol code that is mentioned there. Okay. As a source service access point, which is kind of, as I said, is IP or ARP or something. There's a code for all of them. Same thing for destination. This is an example. IP has SAP this. NetBIOS, for example, see, old days is novel IPX network is an old picture. These protocols are no longer almost there. NetBIOS is still there in Windows. I think so at least. Novel IPX, Novelist company has gone off basically. But this idea, everyone will use the thing 802.2, and this DSAP or SAP fields will contain the values of this protocol. It's similar to the type field, not similar, kind of almost the same as the type field. Okay. And under 802.3, you have these different things with the different physical layer characteristics, which identifies the connectors, media, encodings, all those things, signal levels, all those things. And these modes of operation that is specified using the control bits, you have unacknowledged connection slash. So this is similar to Ethernet, no acknowledgement, no flow error control. Okay, only error detection, discard this. You can do connection oriented, which has everything. You have acknowledged connection and no connection is but acknowledgement sent by receiver. So this is the mode, for example, which does all of those flow controls, error controls that are technically part of data link. But as I said earlier, we don't do it for Ethernet because even if I make the link perfect, there can be drops at the routers connecting those links. So anyway, I have to do something at the higher layer. So I said, why do it then at the lower layer? Because even if I do flow control between two endpoints of the link, I still need to do flow control between the two endpoints, my machine here and somebody's machine at the US. So why worry about doing it at the lower layers? Don't spend time there. Do it once at the higher layers. Okay. And these things, you can just mug a little bit if anybody asks you, basically. So you can do go back and selective reject, all those ARQ techniques. So it's a full stack, basically. As I said, it's not used for, okay. So IP networks works on Ethernet 2 directly, and 802.2 is not much used nowadays. Okay, we don't say too much use, but it's there still in some cases. Okay, so I want to now summarize what was there that you will see and what is now. So your Ethernet switches, they're commonly called L2 switches. As I said, they're L2 switches because they're L2 address. They switch based on the L2 address. They look at the address, this L2 address, the MAC address, and they switch based on it. Now the switches broadly can be of two types. These are low cost switches, unmanaged and managed. Okay. What is managed? Managed switches can be monitored and configured remotely. Okay. So there is a protocol called SNMP. We may do it, simple network management protocol. So managed switches, for example, I can sit in CIC and I can look at your switch in, let's say, RK, particular switch, and I can figure out without going there doing anything, oh, this port is down, that port is up. Okay, I can find out the traffic rate at those ports. I can reconfigure the ports. I can block a port sitting at my CIC office. So there, when you have a large number of switches, okay, if I have managed switches, then I can actually monitor and configure them remotely without having to physically go there and do them. And for even if you have not remote, okay, higher end switches actually you can monitor almost everything. For example, the switch should not get too hot. You can actually, for higher end switches, you can monitor the temperature inside your switch. And you can, there are nice softwares which will do this, that you can monitor the temperature in your switch, and if the temperature goes above something, it will raise an alarm, send you an SMS. You can design software like that. So you sit in your room, in your network control room, some AC has broken down or something, temperature is rising, you will get an SMS automatically. Okay. So those are managed switches. Obviously they are higher cost, but easier to build. And as I said, 10-100 Mbps switches are still available, but most switches from common OEMs are now gigabit switches. Then each port speed is 1 gigabit per high. Okay. But they're downward compatible to 10-100, so there will be auto negotiation. Even if you connect like 100 Mbps NIC to a 1 Gbps port switch. Modern machines, laptop, new ones that you buy all come with 1 Gbps NICs also. And for, okay, let me come back to this. So let's kind of draw a picture. So old days. Okay. Basically simple thing. You had hubs. Hubs. Okay. And again, this connection can be, STP was there for a long time. Okay. And then you had machines connected to all of them maybe and so on. Okay. And then from some of these hubs, there were switches. So these are your backend switches. But these were usually L3 switches that we'll discuss later. So the LAN edge point that you saw were mostly hubs, okay? Some L2 switches, okay? This I should not say only L3 switches, so there can be some L2 switches. The picture is not very clean. Okay? And then backend switches, higher and higher capacity switches and so on. Okay? So once I do IP and all, I'll draw to some extent your kind of a schematic of your IP network. Basically, probably the conceptual. So this was old days. Now there is no how. Okay. So if you switch, look at the switch. Okay. There will be, when you buy a switch, you will see either it is with respect to explicitly mentioned or will be mentioned in terms of speed. So there will be some uplink ports and some downlink ports. Okay. So uplink ports are the higher speed ports. Okay. So I don't know why this line comes. So let's say these are all 1 Gbps ports, all 1 Gbps. And these you connect to your machines, laptop, whatever it is. Okay. And then, as somebody noted correctly, that if all of them send through this, okay, then if I connect a switch with a switch, okay, then that switch will not be able to take the data. Okay. So I'm going to connect the uplink ports of this to a higher data rate port out there. So this lower downlink ports will, the downlink uplink is a term. Okay. You kind of, every switch that you buy, okay, will give you some ports of a lower capacity and some ports, a few of them, with a kind of a higher capacity. It depends on how much money you spend, first of all. It may not. All of them can be 1 Gbps. But you see, if I'm connecting to a hostel, for example, okay, 1 Gbps is a huge speed. So I get this 1 Gbps port to connect to your LAN point in your room, but then your laptop is never going to send me 1 Gbps. It is never going to send me more than a few tens of Mbps max. Okay. So then 1 Gbps uplink is sufficient for it also. So I can connect any of them. Because even if I have, like, 16 of them, 24 of them, and not all of them are working at tens of Mbps all the time, so 1 Gbps may be sufficient. We have other ways of expanding with 1 Gbps. But then if I think about the backend switches, okay, it is really, there's a lot of 1 Gbps traffic coming from other switches, basically. So each of these 1 Gbps coming from switches, okay, that generate a total of 1 Gbps as per my plan. Then I get some of them, then I need to put maybe 10 Gbps ports. So now your LANs will be basically collection of switches only, where downlink ports, which are lower capacity ports, are connected to, I would not use the word only machines. Machines or switches, you have to estimate that they cannot generate more traffic than that usual. Okay. And then there will be, for that bottleneck thing that we discussed, in every port, every switch, if you spend enough money, there will be some ports with higher capacity. And those are the ones you connect to use. If you think that there's a lot of traffic coming in and I have to send all of them through here, they will go here. So that's how we take care of the bottleneck. But there is another issue from what we have learned so far. I know it's a long class, but I want you to pay attention. Okay. So you see, based on what we learned about sharing media and so on and so forth. So suppose these two machines send something to this machine together. Then there should be a collision, but this cannot receive the two things together. So this machine sending to somebody else and this machine sending to this, are separated out with a switch. But what if two machines send the same thing to the same port? Okay, then there is a collision. Okay, but then also what the modern day switches will do, they will add a buffer with each port. Okay, so your switch with each port will have a buffer. Okay, when the packets come, it will be put in the buffer. Then there's the engine that will look at this thing. Okay, there will be many ports and so on. According to some policy, look at these packets and say send it to the output port where there is another buffer. So you'll pick up. So even if both of them are sending to this, okay, it doesn't necessarily cause a collision, drop-off packets or anything, because these packets are now buffered, and then this will be buffered here. Okay. But old switches, we have duplex using CSMA operation. The switch can also generate a jamming signal. I'll get back to you on that jamming signal part again. Basically, I think modern day switches don't send the jamming signal. Okay. So modern day switches have kind of evolved. As I said, there are buffering. So that manages the data rate to some extent. Also, you will have higher capacity ports which will manage the data. The difference in the thing for the bottleneck. So all slants are now switch slants. The switches again, the capacity of the switches will vary. After we do some more things, I'll actually show you a spec of a switch, both an L2 switch and an LC switch, and we'll see how complex they look this. But there I will show you this port thing. I'll show you how to calculate what you need basically. And you'll see that there's a relationship between this port speeds and this uplink port, the higher data rate port speeds basically. So, and LANs have gone on to, so 10 Gbps is fairly common, though not for your end connectivity, the back end connectivity. You have 40 Gbps LANs, you have 100 Gbps LANs. I think work is on for 250 Gbps LANs also. I'm not very sure. I'll check on that, 200 or 250. But again, those are for like very back end connectivity in data centers and so on and so forth. In our IIT, for example, we have up to 10 Gbps LANs basically. Okay. And finally, modern day LANs have become even more this. This is there for quite some time. There is something called virtual LANs or VLANs. So the picture that I've shown you so far, okay, it seemed like, so if you had 3 switches and then switch connecting switches and then other switches out there and so on, okay, other things like there. The picture that I've given you so far is that all of them are on the same line. It is just that I could not connect them to one switch, so I kind of expanded this. You can do that, but modern day LANs offer you something called a VLAN. Okay, I'm not going to go into details. It's a very important thing, but again, we have just the X amount of time for everything. So with VLANs, I can do this. Okay, I can say only these 2 ports in this switch, these 4 ports here, and these 3 ports here are in one LAN, and I give it a LAN ID, VLAN ID. Okay, but then this other 2 ports, so this is LAN ID. Okay, this is LAN ID. But then these other 2 ports here, 1 port here, and 3 ports here are in another LAN, LAN B. So not only can I, have switched LANs, but then I can kind of segregate the ports inside the switches to say that my LAN is actually not all these switches, but my VLAN 1 is actually this ports in these switches. I can configure the switches like that. And with a managed switch, I can configure it remotely. Okay. So now, if I send a broadcast packet for that VLAN, it will only reach this port. The other ports will not receive it. So it's a little bit more complex. That's why we are not going, you will not understand much about it. But just know basically that old days were hubs, no longer there. All LANs are switched LANs now. The switches will have, if you want to pay some ports with higher capacity, so you can actually take the downlink traffic and just kind of put them together and send. There will not be much bottleneck. There will be buffers associated with ports to buffer their packets for the speed mismatch. And that it's not necessary that all the ports of a switch must be in the same LAN. In a tree structure with topology, any LANs topology, we can actually have VLANs, virtual LANs, which kind of segregates the ports of the different switches into different lines, so that different VLAN broadcasts will reach only those ports in that particular VLAN. So that's all we have for LAN. I request, it's a long class, I understand. Thank you. I request you to kind of go through the material, but other than mugging, kind of think about, as I said, there's a lot of confusing things out there. You will see something in textbooks a lot, and then I will come back and say, but you see, this is no longer needed. But you need to understand why it is no longer needed. What has happened? So is it irrelevant? Absolutely not. Okay. You will still find these uses different places. As I said, connecting computers is not the only network out there in the world. Okay. You need to connect small devices and so on. And you will find the concepts in many places. So when you design new protocols and all, you need to know what has happened, what was the design, justifications, how did you choose the parameters and so on. Okay, so that's all I have to say today. If you have a question, ask me. Otherwise, the class is over. Very thin attendance. I don't know what is happening. But I hope at least that you are here. The class is studying. Okay, so if there are any questions, you can ask. I'll be here for another 5 minutes or so. Otherwise, you can go. Class is dismissed, so you can go.